Hello and welcome. My name is Sean Lacey of Lacey Maths and Stats Consultancy, and these set of videos are on presenting statistical test results in RStudio. The focus for the videos are single sample tests, two independent sample tests, and two dependent sample tests. The rationale for doing these videos is based on when I normally would facilitate statistical training courses. I find that a lot of the time, or the time that we have anyway for a particular course, will be spent on outlining the appropriate descriptive statistics to apply, the particular tests that are required based on assumptions being met or violated, and then how to interpret the results and so on. What I find is often that where there isn't a lot of time for is how to actually present the results, as in the table. And I suppose for me personally, I'm not a fan of kind of creating a table manually in Excel or Word. I much prefer exporting my results from RStudio into Excel and then bringing that into Word if need be. I much prefer kind of having the transparency or having the track record of how I have my results generated in RStudio and how do those results from RStudio get to my report. I like having that. Sometimes you have to copy and paste, but I try to avoid that if at all possible. And I suppose these videos is just showing you or demonstrating ways of when running off particular tests, how we can, I suppose, use the test results or how we can extract the test results for presentation purposes if required. And these are just, I suppose, demonstrations of ways that I would present results, and I think it's more just kind of noting the technique hopefully might be of use. You might necessarily want to present all the results that I'm presenting, or you might want to present more, but hopefully you'll see that from the script that I'm going to be generating that that you can expand or lessen it depending on what your own requirement is. The focus for I suppose, the videos will be the one sample, I suppose, the one sample T-test and the corresponding non-parametric test, which will be the Wilcoxon test. The two, the independent T-test and the non-parametric version, which will be the Mann-Whitney U test, and then finally a paired T-test and its non-parametric version, which will be the Wilcoxon test. So for each set of video, we're just going to look at the two tests. Okay, so for this video here, we're going to focus on the one sample T-test and the Wilcoxon test. The data that I'm going to use for this is the data that we would have used in previous videos. So in a video that I would have uploaded to YouTube on introduction to using dplyr and tidyr packages to filter and convert from wide to long, I would have basically created this data frame here. So what this relates to here is where you have 16 participants that were on a particular diet over the course of how many? 4 months. And over the course of the 4 months, so their triglyceride measurements were taken in milligrams per deciliter at baseline and at the end of 4 months then. And for the case, this here is there are 7 females and 9 males. Okay, so I'm just going to use this data frame that we actually have already used in previous YouTube videos and just, I suppose, focus on particular parts to it for the purposes of doing these tests. So for, I suppose, for this, the videos, it's not necessarily, I suppose, trying to interpret the results of tests or trying to say, look, do we satisfy assumptions or violate the assumptions? The focus for these videos here is how do we present the statistical results at the end. The statistical results that I'm going to focus on will be where there's a difference. So whether it's a mean difference or median difference, then the confidence interval of the difference, the p-value, and the effect size. So that'll be the kind of the way I'm going to just look at it. Now you might decide for yourself that you might want more information or less information, but here hopefully that you'll see that the script that I'm going to generate here, which is available for you in the description underneath this video, might be of use to you. Okay, so and as always, what would be great is if you find that I suppose the information in this video and the follow-up videos are of use and of good, I suppose, of interest and of benefit to you, that you might like and share or even subscribe to the channel. That would be much appreciated. Okay, so for the first part we're going to look at is we're going to look at the single sample. Okay, so we're going to look at where we're just having a single measurement and we're going to be comparing that to a population parameter. So these are kind of just where I'm making up different scenarios. So I didn't necessarily want to be generating loads of types of data sets for this. So I just want to, I suppose, look at this data frame that we have here, or this data set, and just kind of filter it to break it down into a smaller data set and then apply a particular test. And again, the focus for the videos is how to present the results at the very end. So for the single sample Ttest or the Wilcoxon test, I'm just going to focus on these first 16 measurements we have here. So we're just going to look at triglyceride level measurements at baseline, okay, to see is there a difference. And I'm going to just do a what if scenario. I'm going to say, look, where the population parameter is 130 milligrams per deciliter. For whatever the interest is in the study, that is just a number I've just picked out, okay? So that's going to be the idea. So we're going to look at these 16 numbers here and try to determine whether or not they're different from 130 milligrams per deciliter, okay? So here in the so I've the script already prepped because I suppose for the purposes of the video, you can obviously, as with life and order, there can be a lot of scripts, so it's not necessarily stuff that you'd write off the cuff. The first protocol will be in making sure that you have the required packages for the range of videos. So I'll just talk through, I suppose, the purpose of these, and as you're working through the script, you'll find that I'll always kind of state the library that I'm using for a particular function as well. I find that just kind of good and early, a bit of a refresher when I try to familiarize, I suppose, with the various packages that are needed for particular functions and so on. So the first one is read Excel. So this is to import data from Excel. Then it's going to be the dplyr package. The reason I want to use the dplyr package is so I can filter the data frame that is in Excel, so I can kind of just reduce it down to, I suppose, the data that I want to focus on for the particular tests. ggplot, I just feel that before going off and doing a statistical test, we should always just generate a graph just to kind of see, look, what is the actual data. Again, the purposes of the video is more the end result. How do we present the Ttest results or the non-parametric version results? But I still think it's good just having an idea what type of data we actually have. So we're just going to look at ggplot. Tidy-OR, the reason to do Tidy-OR is just it's good to, I suppose, when you think of graphing the data using ggplot, it's good to have it just, I suppose, a few numerical descriptive statistics as well. So I'm going to just look at generating the mean, median, the skewness, and whether or not the data is normally distributed. I'm going to use the summarize function through the tidy-OR package for that. Psych is going to be needed for because of skewness. LSR is going to be needed to determine the effect size, which is the standardized mean difference for the one sample t-test. XLSX is for exporting the data to Excel. Then RStatX is just going to be for the non-parametric test we're going to use. We're going to use the Wilcoxon non-parametric test. There's a few packages that we could use for that, but I'm going to use the RStatX one, and the reason for that is because that will also calculate the effect size for the Wilcoxon test first as well. So that's there's a nice function in that package for that. And then the last package that we're going to need there is the CAR package, and the reason for that, and that won't be for this video, will be for part 2, where we're going to be looking at Levine's test. Okay, so it's just, I suppose, for Levine's test, I'm going to just use the CAR package. So I'm going to first, I suppose, look at the installing those packages just to make sure everything's okay. So it's just going to be installing the packages and then loading the libraries, and it's just taking its time there. And as always, you'll see that in the description to this video, there's a link to a Google Drive, and on that you'll have the syntax that's generated in the video, and you'll have the data set as well. The diet study version 2 is what I've called it. So you'll have that there that you can actually be, I suppose, replicating these steps here. I'm just going to import the data. Obviously, when you're importing it yourself, your directory is going to be different to mine. And this is where we actually have then the long, so when I'm importing, I'm calling it long. And so this is where then we have the 80 measurements, so the 16 patients over the 5 time points, okay? And for the purposes of doing the one sample t-test, is I'm just going to look at the baseline measurements, okay? So I'm going to just filter the data to focus on the baseline time point. And when I do that, I'm going to call that single. Okay, so that what that's basically going to do is it's going to actually just cut this data frame where it's going to just focus on the first 16 subjects. Okay, so it's 16 data values. So it's going to just look at the first 16 rows here. But then I suppose just to condense it and to kind of make it very specific to what is needed for the one sample t-test, I'm just going to then select the patients, sorry, not the patients, but the participants, the 16 participants ID and the triglyceride measurements. I don't necessarily care about the gender. Time is going to be baseline, so I don't need that. So it's just kind of, I suppose, just tailoring the data to my specific needs. Okay, so using the dplyr package for filter and then for select. So filtering is just looking, so line 47 there is to just focus on the baseline, and then line 48 is kind of just, I suppose, condensing the data frame then. I'm going to call the results 1, and this is then where we have the 16 participants at baseline. Okay, now didn't necessarily need the participant ID, but I just think for good practice, and I'd be a big advocate of trying to promote good practice in statistical analysis. I always think, look, even though that our end result for these videos here is the statistical test at the end, it's still kind of good to be kind of doing the steps along the way correctly. Okay, so it's good to basically keep track of who your participants are. Okay, so that's that. So since we're just looking at the data for the first time, and just I feel it's good that you just draw a graph to see what type of data we have. So here I'm just going to draw a bar chart, sorry, not a bar chart, a box plot with error bars on it. So I'm going to be a box and whisker plot. I generally do it in two steps. That's how I would do it. I do it in the first step here, which is where I nearly generated it by default. And then I'd look to see, look, am I happy with the scaling? Am I happy with the labeling of the axes? So for me, even though you could generate a graph all in one step, obviously with the script, I always like kind of doing it in two steps. And then this is the graph. So this is the triglyceride measurements for the 16 participants at baseline. Okay, and what we can see here is obviously this is your 5 points. So you have your minimum value, your first quartile, you have your median, third quartile, then you have your maximum value. And what we're eventually going to be doing is we're going to be comparing the 16 measurements that are described in this box plot to the number 100. The number 100 will be our population parameter. Okay, so that's that. Then let's generate some I suppose descriptive statistics and get an idea to whether or not our data is normally distributed. So I'm going to use the tidyr, I suppose, package library here. I actually should nearly even type it in here, tidyr, because that's what's used for the summarize function, and then psych is used for skewness. So you can just see here I'm working out the mean, the median, and then I'm trying to determine whether or not the data is normally distributed. I'm using a 5% level of significance when I'm doing a test of normality, and the test of normality that's being done is the Shapiro-Wilk test. And I'm just actually, I have put together some script here where it's going to generate what the p-value is and then tell me based on that p-value to whether or not the data is normally distributed. So this is how I'd like to generally do things, and I suppose I would have expanded on this in the previous video that would have been uploaded onto YouTube as well. Okay, so what we actually have here, maybe if we just expand here, so we can see here we've said 16 participants. Here's the the mean triglyceride level at baseline, the median, the skewness is close to 0, and then it's telling us the data is normally distributed, whereby the p-value is greater than 0.05, the p-value is 0.2767. Okay, so our data is normally distributed. What that will mean then, when it comes to the type of test that we're thinking of going to apply, we will apply the one sample t-test. Now, for the purposes of this video, I'm actually going to do both tests just so we can just see how we would handle both tests. But strictly speaking, we only need to do the one sample t-test. So when I do the Wilcoxon test shortly, that is purely for illustration purposes. Okay, so here we are. So we're going to just do one sample t-test. So here we're going to see whether or not it's different from 130 milligrams. So we're doing a t-test and calling all the output that I'm going to get from the t-test. I'm going to call it res 1.1. So we're going to have over the videos, we're going to have kind of 6 res results. Okay, so 1.1, 1.2, 2.1, 2.2, and so on like that. Okay, so it's going to be a t-test where I'm looking at the baseline measurement, comparing it to 130. The confidence level of 0.95, that's not required. It's going to be default. I just like stating it. I just think it's good, especially maybe just to highlight it to a user maybe for the first time that is the level of significance. It's the default level of significance, as in 5% level of significance. It's the default one, but it's more a case of to highlight to a user if you wanted to work off a 10% level of significance, then you should be working off a confidence level of 90% when doing the test. Okay, so that's not a requirement, but I just think it's nice to actually have it for completeness. When we run off the t-test, we end up with this result. Now, and not the focus for the video is not to kind of dwell on more on kind of interpreting all the results, what the null alternative hypotheses or anything like that. What the focus of this is basically just seeing, look, that we have a p-value here. I want to generate a table that will present that p-value. And we have a mean down here. It's telling us what the mean is, and I want to compare that mean to 130. Okay, so you'll see where I'm kind of going with this when it comes to the first end result, and then that will kind of keep it in line then for the later one. Okay, what can be often useful for when we report statistical results. So when we report a statistical result, that's what we have is a p-value. A p-value will ultimately tell us whether or not the result we have is reliable. It does not necessarily tell us how good the result is. If we want to know how good the result is, we want to measure do a measure of strength, which is your effect size, called your standardized mean difference. Okay, so for the standardized mean difference, I'm going to use the LSR package, and I'm going to use Cohen's d function then. Okay, so for Cohen's d, so this is calculating the standardized mean difference. We have a classification of 0.2, 0.5, and 0.8. If your Cohen's d is less than 0.2, then the difference that you've observed is negligible. If it's between 0.2 and 0.5, it's seen as a small difference. If it's between 0.5 and 0.8, it's a moderate difference, and if it's greater or equal to 0.8, it's a large difference. That is the Cohen's d classification. So if we load the LSR library, we can run off the Cohen's d and state that we're looking at 130, and I'm just rounding it to 2 decimal places. So that's what the first part is here. I'm just going to run off these bits here. So that tells me here's my effect size then, rounded off to 2 decimal places. And then the second line of code is just classifying it. Okay, so this obviously takes a bit of time, the first time to kind of write it up, but then after a while it's just going to be the same kind of, I suppose, script that I would use. So this is telling me that the difference that's observed, the standardized mean difference of 0.29, is classified as small. Okay, so then it's a case of pulling all that information together. So what I would see here is there's kind of 4 types of things, results that we actually have. We have the mean difference. We have a confidence interval of the differences. So up here in the t-test, we have the confidence interval. I'd never actually highlighted that, but that's something we're interested in. Then we're going to have the p-value, and we're going to have the effect size. So I'm just going to maybe just highlight this guy here. I'm just going to put brackets around this so you can actually see that these are the statistics that I want to present. I want to present the mean difference. I want to present the confidence interval, the lower and the upper, and then the p-value, and then the effect size. Okay, so this is just, I suppose, an illustration. It's a guideline. It can vary depending on the type of study that I'm doing to maybe what descriptive statistics or what statistical test results I would report. But this is just generally how I would, I suppose, try to generate statistical test results. Okay, so here, so these are I suppose, the labels that I'm applying, and then it's a case of how do I actually get the results. So if we look at res1, so res1 was the output that we have from the t-test. If we do $, which is kind of get its attributes, so if I just type that in down here even, res 1.1, $, these are the various outputs that we have here. So you can go here to estimate, and the estimate will output the mean. Okay, so that's what we have here. If I go back here, if I do the $, here, and if I do confidence, you can see that there's a confidence interval here. Here's the confidence interval. So that outputs the upper and the lower. If I only wanted the lower one, I could do a 1 at the end, and that would just output the lower confidence interval limit. Okay. If I come back to this res1 again, res 1.1. If I do the $, there's going to be a p-value. So that'll output the p-value. Okay. I just think you'd want to round that p-value, so you can just see in the script that I put in here, I'm stating it rounded to 3 decimal places. And then the last thing then will be effect size. So if we just talk about these ones then. So I'll just highlight them without running them. So the first one here is where I'm looking at the mean difference. So I'm taking the mean that's observed from the t-test. I'm subtracting 130 from it, and that'll give me the mean difference. Then if I look at the confidence interval of the differences, so this is the lower limit one. So I take res 1.1, $ confidence interval, and I use the first one, which is in the square brackets 1. I'm minus 130 from it, and I'm just rounding the answer to 2 decimal places. I do the same up here for the upper limit. Then for the p-value, I'm taking the p-value from the res 1.1 result. So that's what I'm doing here. And then I'm rounding it to 3 decimal places. And then I'm looking at the effect size kind of classification as well. Okay, so that's what that is. Then I put all that information together in a data frame, which I'm calling output 1.1. And these are the results we have. Okay, so we can see here from these results, the mean difference is 8.4. Obviously, it's missing the unit. I'm going to have to kind of put in that bit of information, but what I'm more interested in is the data that I have here, and then I'm not going to be typing this data up, okay? So you have the mean difference, which would be 8.4. You have the low confidence interval, so 95% confidence interval, the lower bound, -7, the upper bound, 23.9, the p-value of 0.263, and then you have your effect size, which we're classifying it as small, being 0.29. Now, you could put in some comment here with the p-value that you're going to fail to reject the null hypothesis if you're working off a 5% level of significance. But look, I generally don't say something like that in a table. I would just kind of state the p-value, and then underneath and kind of in the text, kind of referencing the table, I'd kind of give whatever my conclusion is. Okay, so this is where I've kind of, I suppose, have brought all the results together in one place, and now what I would next look at doing then is bringing that into Excel. Okay, so exporting it to Excel. So I'll just show you, I suppose, run it off here once, and for the later ones I won't always do this. Okay, so you can just see here I'm writing it to Excel, so like this. So I'll come to the folder that I've set up here, and here I have 1.1, output 1.1, and here it is. Now there's always going to be a small bit of formatting. I would have talked about the formatting that sometimes is needed in a previous video. Okay, so if you wanted to check that out. but this is kind of ultimately where you're at with this. Okay, so you can just see here you've your mean difference, and then you've your confidence interval, your p-value, and your effect size. And again, it's all in Excel. I'd probably put in a triglyceride measurement up here and with its unit and just state something here. And then I would look at copy and pasting that into, probably look at doing borders and shading first, and then copy and pasting it into Word, and then job done. Okay, so what I like about this is I haven't typed up any of the data at any point. I have a track record of how I've generated this table. Okay, and it takes a bit of time, I suppose, to generate the table for the first thing, but you'll see then that it's actually quite straightforward once you have the script set up. Okay, and you can see even from this video here that it's obviously taken a bit of time to get to this point. But when we go off and just for illustration purposes do the Wilcoxon, you'll see that's going to be a lot faster. Okay, so that's how I would look at presenting the, I suppose, the statistical test results for one sample t-test. Now what I want to do is just look at the Wilcoxon test. So the Wilcoxon is if the data was found not to be normally distributed. Now in this case, the data was normally distributed, so doing the Wilcoxon test is not a requirement. So I'm purely only doing this for illustration purposes, I suppose, just balancing it, okay? Because there's no point me just generating script for one sample t-test, and then in your own data, you'll actually find that your data is not normally distributed, and you need to do a Wilcoxon test. So I just want to kind of just show you the script for that, and then that'll be the end to this first part of the video. Okay, so what I'm just saying here is, what if the data is not normally distributed? Well, if the data is not normally distributed, what you're doing then is you're doing a Wilcoxon test. There's a few versions of this in R. There is a Wilcox.test, similar to the T.test above. I like doing the Wilcox_test. I like that one from the RStatics package because of the effect size that I can get from this package as well. So it's a case of going to the one package for all this information. I find that a use. Okay, so you can see here I'm calling this res 1.2. I'm looking for and focusing on the baseline measurement and comparing it to 130. I'm asking it to do working with a 5% level of significance. Detailed equals true. That's not a requirement. It defaults to detailed equals false. But by me saying detailed equals true, that's going to give me the confidence interval for the results as well, which is something that I need then further down. Okay, so I'm just going to run this off here. And here we have it. Now again, this is not a requirement. This is really for an illustration purposes. Okay, so we can see the various information. So we have the median here at this end, what measurement we actually have. There's 16 measurements. Then we have the test statistic results. Here's our p-value of 0.289. Then we have our lower confidence interval, the upper confidence interval. So I think that's quite nice information. So that's kind of the information I want to generate then. And then the next thing is I want the effect size. So if I'm looking at the effect size, it's going to be the Wilcox F size function. Okay, so I'm going to do that. Yep, there it is. Okay, so here what we have is, it's a nice output. Okay, it's different from the LSR one, so it tells us what the effect size is, and it tells us how to classify it. Okay, so the classification for the effect size here is 0.1, 0.3, 0.5. So if your or effect size, so or is the letter, the effect size is less than 0.1, it is deemed as negligible. If it's between 0.1 and 0.3, it's small. 0.3 and 0.5, it's moderate, and greater than or equal to 0.5, it's deemed as large. Okay. So you can just see when we run off the Wilcox_F size function, we get numerous outputs. So I just want to focus on the effect size output. So this is where I'm just focusing on that subpart, okay? And then I want to round it to 2 decimal places. So that's what this line 99 does. And then I want to classify it as small, moderate, or large based on the value. So this is similar to what I did with the t-test. And that's what I have here. Right? That actually didn't work there. Why did you not work? So let me just run those guys off there 1 second. That should work fine. There it is. Okay, so I'm not too sure what happened there, but anyway, there we have it. Okay, so 0.27, and that tells us then that our effect size here is going to be seen as small. Okay, and then we're just looking at presenting it. Okay, so I'm going to keep to the same format here. The only thing that's different is now if the data is not normally distributed, we should be talking about the median as opposed to the mean. So it's looking at the median difference. Then obviously we have the confidence interval of the median difference, then the p-value and the effect size. So you can see here that all these results, so I'm taking the results from res 1.2 and taking $sign estimate, so that's the median. I'm minusing 130, so that'll give me the median difference. Res 1.2 confidence interval low, I'm minusing 130 to give me the lower confidence interval difference for the median, the upper confidence interval difference, the p-value rounded to 3 decimal place, and then the effect size. So with the labels and so on like that. So I'm just going to generate that here, and there it is. Okay, so we have the median difference of 7.5, the confidence interval of the difference, so the median confidence interval of the difference of -7 to 26, so it's the 95%, and then we have a p-value of 0.289, and then we have the classification of the effect size, okay? And so this tells, again, I suppose the purpose of the video is not necessarily to dwell on the interpretation. The purpose of this video is more to focus on just how to, I suppose, pull all the results together. If people were interested in, I suppose, a video on the presentation, not the presentation, but on the interpretation or the explanation around it, I'm more than happy to facilitate something like that. So if I'm more than welcome comments there. If people want to put comments below this video. I mean, I think comments on maybe you might have a different approach to, I suppose, presenting test results and more. I think that's great. If you do and you want to share it, that's absolutely brilliant. Then here is just the last step. Here is just where I would write it then to Excel. I'll just show you that. Okay, even though I said I wouldn't do it again. So here you can see I'm writing it, and there it is. There are the results. And I just think that's great, because ultimately what we have here is we have the track record of all those steps, and that's what I think is just brilliant with R, and it's something we should try to be using to our advantage, not necessarily copying and pasting results, or definitely not manually typing results. There's definitely ways around that. Okay, so look, that's the end of the first part. This is going to be a three-part video series. This next part we're going to focus on the independent t-test, so we're looking at 2 independent groups, and then the third part we're going to look at 2 dependent groups. Okay, so hopefully you find it the video of interest. If you do, I mean, subscribing it will be the channel will be absolutely brilliant, and ultimately then if you subscribe you'll get updates on when the latest videos are out and so on like that. Okay, but for the moment, all the best.